create. So as you can see, this demo instance is currently provisioning. Welcome to this demonstration on moving a VM between OCI regions using full stack disaster recovery. So let's get started. I'll take you to the OCI console, and currently I am in the Phoenix region. So very quickly, I will create a VCN. I will name it demo VCN, and this is going to be the CIDR block. Click on create VCN. I'll also click on create subnet, demo subnet. This is the CIDR, and I'm okay with public subnet. Click on create subnet. Okay, so you see that the subnet is currently provisioning. Okay, so the subnet is now available. Now let me create an instance, and I will call it demo instance. I'll keep everything as default. Select this particular existing virtual cloud network and this subnet. No SSH keys. Click on create. So as you can see, this demo instance is currently provisioning. In the meantime, I will go to the Ashburn region, and here I am going to create the network as well. So create a VCN. I'll call it test VCN. This is the CIDR. Create VCN and click on create subnet. All right, so this is perfect. Now, if I return back to Phoenix, I see that this instance is currently running. So what I also need to do is, if I go to the storage, click on block storage, I will be able to see the boot volume for my demo instance. So I also have to create a volume group. So call it demo volume group, select an availability domain, click on next. Here you need to select the boot volume, which is demo instance boot volume. Click next. Here you have to enable asynchronous cross-region volume replication to the Ashburn region. So select the first availability domain, click on confirm, click on next, and click on create. So I will wait for this volume group to get provisioned. In the meantime, under resources, if you click on boot volumes, you will see that this volume group will have one boot volume, which is your demo instance. the meantime, under resources, if you click on boot volumes, you will see that this volume group will have one boot volume, which is your demo instance boot volume. All right, so this demo volume group is now available. So now I also need to create an object storage bucket. Click on create bucket. I will name it FSDR bucket. Click on create. I also need a bucket in the Ashburn region. So click on storage. Under object storage and archive storage, click on buckets. Create bucket. And give it a name FSDR bucket. Click on create. Okay, so now you see that this bucket is created. Let's return back to Phoenix and now click on navigation menu. Click on migration and disaster recovery. Click on disaster recovery. So under disaster recovery, click on DR protection groups. So first I will create a DR protection group for the Phoenix region. Create DR protection group. So DRPG Phoenix, this is the compartment migration demo. You have to select the object storage bucket. So FSDR bucket. Now we are not configuring any role and we are also not adding any member. So we are just creating a DR protection group. Click on create. So this DR protection group is currently creating. In the meantime, I will also create a DR protection group in the Ashburn region. So click on navigation menu, go to migration and disaster recovery, click on DR protection groups under disaster recovery, create DR protection group, and name it DRPG Ashburn. So this time select FSDR bucket. Again, we are not configuring any roles and we are not going to add any member. Click on create. Okay, so this DRPG Ashburn is also creating. In the meantime, you see that DRPG Phoenix is now active. So we will wait for this DRPG Ashburn to be active. Okay, so now this DRPG Ashburn is also active. So let me go back to Phoenix, click on associate and select a role. I'm going to make it primary. Now it is going to ask you the peer region. So the peer region is going to be Ashburn, US East. And what is going to be the peer DR protection group? That is going to be the DRPG that we created in Ashburn. Click on associate. You see that this is currently updating. So now you see that this DR protection group Phoenix is the primary. And if I go to Ashburn, let me refresh it. And in the Ashburn, you can also see that the DR protection group that we created is the standby. So the role is standby. Now let me return back to the DR protection group in Phoenix. Under resources, I'll click on members and click on add member. So first I will be adding compute. And let me select the instance that is running, which is demo instance. The compute instance type is going to be moving instance. And here I also need to add the VNIC mapping. So this basically is the mapping between the VNIC for each instance and a destination subnet. So click on add VNIC mapping. So this is our VNIC demo instance. And what is going to be the destination subnet? This is going to be the test subnet that we created in the Ashburn region. So no need to configure these. Just click on add. Now you need to click on I understand that all existing plans will be deleted. After that, you can click on add. So we have added one member to this DR protection group Phoenix, which is our primary. And you can see that this member is the demo instance. The category is compute instance and the state is running. So we will wait for this update to get completed, and then we are going to add another member, and this time it is going to be the volume group that we created, which contains the boot volume of the demo instance. Okay, so now you see that this DR protection group is active. Let me add another member. The resource type this time is going to be the volume group. And we have only one volume group. So let me select that demo volume group. Click on add. Again, it is going to go back to the updating stage, and we will wait for it till the status becomes active. Okay, so now the DR protection group Phoenix is active, and you see that we have added two members. Okay, so now we are going to go back to the Ashburn region. So here we are going to create a plan. So let me call it DR plan, and the plan type is going to be switchover. Click on create. So you see that this DR plan is getting created. So in the meantime, this DR plan is getting created. I will open up a duplicate tab, and I will take you to the instances page. And you can see that currently there are no instances that are running in Ashburn. Phoenix region where you have this demo instance running. So as you can see, I am back in the Ashburn region and this DR plan is currently active. So let me run the pre-checks. This is the DR plan. Click on run pre-checks. So you see these are the pre-checks, and you will be able to see the state when it started, when it ended, and the duration. And currently you can see that these pre-checks currently are in progress, and you can see that the state is succeeded for all of these. Now go back to the DR protection group. Note that we are in Ashburn region. Now we are going to execute the DR plan. So click on execute DR plan. This is the DR plan. Enable pre-checks and click on execute DR plan. So this built-in pre-checks is also going to be included here. So you can see the details over here, the name, the type, the state, when it started, when it ended, and what's the duration. So currently the built-in pre-checks is in progress. And if you want, you can see the details as well. Currently, all of them are in progress. So these all succeeded. Now it's going to stop compute instances. You see that currently it is in progress. So if I go to Phoenix, and because we had one instance running in Phoenix, so now you see that it is stopped. This says succeeded. Stop compute instance succeeded. Now switch over volume groups. So this is currently in progress. Similarly, after this step, the compute instance is going to be launched in which region? Is going to be launched in the Ashburn region. Currently, you see that there are no compute instances. But in some time, you will be able to see the compute instance running in Ashburn region. The compute instance that was running in Phoenix region has been successfully stopped. You can also see here that this pre-checks took around 13 seconds. The stopping of the compute instance took around 25 seconds. The switchover of volume groups took around 1 minute 14 seconds. And currently the compute instance is getting launched in the Ashburn region. So if you click here in the Ashburn region, you see that this demo instance is currently getting provisioned. So you see that the launch compute instances has also succeeded, and now it's basically going to reverse the volume groups replication. And you can see that the reverse volume group replication has also succeeded. Now it's removing the compute instances from the DR protection group. And after that, it will remove the volume groups from the DR protection group. Okay, so now you see that all the tasks have succeeded. And if you see the work request, this has succeeded and the percentage complete is 100%. If you return to Phoenix and if you go to the compute, as I have already mentioned, the compute instance will be in a stopped state. And if you click on storage and go to the volume group and go back to the volume group replicas, you will see one of the replicas getting provisioned. Similarly, if you go to Ashburn, you will see one of the volume groups over here, this demo VG. Remember, originally we created the volume group demo VG in our Phoenix region, but now you are able to see demo VG in Ashburn region. And as I previously mentioned, this demo instance is now running in Ashburn region. So this marks the end of this demonstration where I have shown you how you can move a VM from one region to another using full stack disaster recovery service. I hope you found this demonstration useful. Thanks for your time.
Hello and welcome to this lesson on microservices architecture overview. Let's start by understanding what are microservices. The term microservices is generally meant to describe an approach to software development that involves decomposing application functionality into individual components that can be deployed separately from each other and typically communicate via application programming interfaces or APIs. Microservices basically utilize integration, API management, and cloud deployment technologies, which gives developers the freedom to independently develop and deploy services as per their requirement. Microservices are used to design an application that is multilingual. This helps teams which work somewhat independently of each other. This allows developers to use different programming languages and technologies without affecting the overall architectural structure of the software development. One developer might use Node.js to code specific app feature and the other might use Python. That's absolutely fine. Loosely coupled with other services. In a loosely coupled environment, you can easily work with the least elastic component to address any slowdowns or performance gaps. Loose couplings enables the isolation of microservices that lead to better productivity. easy to maintain, and independently deployable. Following code is easier since the services are isolated and less dependent, which also makes it easier to deploy them in literal pieces without affecting other services. So when a change is required in certain part of the application, only the related services can be modified and redeployed. There is no need to modify and redeploy the entire application. Easily scalable and highly available. Microservices are easy to scale and integrate without third-party services. Although not a simple task, but maintaining high availability with microservices can be done using replication methods like load balancing techniques and using API gateways. Failure resistant. You can build resilient microservices by including fault tolerance policies in your code. For example, in a movie ticket application, different microservices might support scheduling, purchasing, and customer preferences. If one service fails, fault tolerance policies help limit the error and keep it from taking down the whole application. Let's take a look at a microservices architecture for a sample e-commerce application. The API layer is the entry point for all the client requests to a microservice. The API layer also enables microservices to communicate with each other using the HTTP, gRPC, and other TCP/UDP protocols. The logic layer focuses on a single business task, minimizing the dependencies on the other microservice. This layer can be written in different language for each microservice. As you can see, this e-commerce application makes use of 3 microservices. One is coded in Java, the other one in Python, and the third one in Go, which makes it multilingual. The data store layer provides a persistence mechanism, such as a database storage engine, log files, and so on. Developers can consider using separate persistent data store for each microservice. As you can see over here, there is a separate data store for container 2 and there is a separate data store for container 3 that is using Go. Typically, each microservice runs in a container that provides a lightweight runtime environment, and these can be scaled up or down as per the user requirements and managed using the orchestration tools like Kubernetes. Let's understand the difference between a microservices architecture and a monolithic architecture. In a monolithic architecture, the entire application is built as a single unit which contains the business logic, user interface, and data access layer. These 3 services are defined within the application as a single instance. So basically, these 3 services will share the same resources and database, which makes them dependent on each other. Problem here is, if one service within a monolithic application stops working, then the entire application will stop. On the other side, in the microservice architecture, the business logic is organized as multiple loosely coupled services, where each service has their own resources which make them independent autonomous services. So even if a single service crashes, it will not affect the other services running within the application. Let's take a detailed look at how microservices differ from monolithic architectures. So when it comes to unit design, microservices architecture are loosely coupled services, whereas monolithic architectures are designed, developed, and deployed as a single instance. When it comes to functionality reuse, microservices define APIs that expose their functionality to any other client, whereas in case of monolithic architecture, the functionality reuse is very limited. When it comes to communication within the application, microservices makes use of REST API calls based on HTTP protocol, whereas monolithic architectures make use of internal procedures and function calls. Talking about technological flexibility, microservices architecture offer better flexibility as they show support for multiple programming languages and framework that best suits the problem. Whereas in monolithic architecture, you have to write the entire application using a single programming language. Talking about data management, within microservices architecture, every microservice can manage their own data store, hence making it decentralized. Whereas in monolithic architecture, you must maintain a centralized database. When it comes to deployment, microservices architecture can be deployed independently. Every microservice can be coded and deployed independently of each other. Whereas in monolithic architecture, you will have to write the entire code at once and then deploy it. And again, if you have to make some changes, then you have to redeploy the entire application. Which is also why maintainability is easier in microservices architecture as you are managing small piece of codes at a time. Whereas in monolithic architecture, it's very complex to maintain the entire piece of code. Talking about resiliency and fault tolerance, microservices architectures show high resilience, whereas monolithic architecture show low resilience. And at the end, talking about scalability, you can easily scale each microservice independently of the other services, whereas in monolithic architecture, you must scale the entire application. Communication mechanism in microservices architecture. As we all know, microservices are distributed in nature, so to communicate with one another, they make use of inter-service communication on network level. Each microservice has its own instance and processes. Therefore, services must interact using an inter-service communication protocol like HTTP, gRPC, or message brokers like AMQP protocol. Before we design our microservices communication, we should understand about communication styles. In general, there are two criteria to classify these communication systems based on the type of protocol, that is either synchronous or asynchronous, and based on the number of receivers, which can be single or multiple. Synchronous communication is using HTTP, HTTPS, or gRPC protocol for returning synchronized responses. The client usually sends a request and waits for a response from the service, which means client code blocks their thread until they receive response from the service. Talking about asynchronous communication, in this case, these sub-processes are not logged, and protocols that are compatible with many operating systems and cloud environments are used. The most popular protocol for this asynchronous communication is AMQP protocol, that is Advanced Message Queuing Protocol. So when using AMQP protocols, the client sends the message using message broker systems. The popular ones are Kafka and RabbitMQ. Remember, inter-service communication can result in a lot of network traffic. For that reason, serialization speed and payload size becomes more important. So if we are communicating between services internally within our microservices cluster, we might also use binary format communication mechanism like gRPC. gRPC is one of the best way to communicate for internal microservice communication. The second classification criteria of microservice communication protocol is the number of receivers, distinguishing between one or many receivers. In case of a single receiver, each request must be processed by a receiver or a service. One example of this type of communication is a command pattern. And a good example in case of many receiver is the event-driven microservice architecture, which is based on a messaging agent or event bus interface that broadcasts the data updates among different microservices using events. Normally, microservices-based applications use systems that combine different communication styles. The most common type is a single receiver communication via an asynchronous protocol, with HTTP and HTTPS being one of the most used. Alright, to wrap up our discussion on this lesson, we covered what microservices are, we covered the differences between microservices and monolithic architecture. We also saw the different communication mechanisms used by microservices architecture. I hope you found the lesson useful. See you in the next one. Thanks for watching. Hello and welcome to this lesson on containerization overview. I am Mahendra Mehra, your senior OCI instructor with Oracle University. Let's get started. Containerization is a form of virtualization, operates by running applications in isolated user spaces known as containers. Notably, all these containers share the same underlying operating system. The container engine, pivotal in containerization technologies and container orchestration platforms, serves as the container runtime environment. It effectively manages the creation, deployment, and execution of containers. Now let's explore the magic of containerization. Imagine a container as a fully packaged and portable computing environment. It's like a digital suitcase that holds everything an application needs to run. Binaries, libraries, configuration files, dependencies, you name it, and the best part, it's all encapsulated and isolated within container. In olden days, running an application meant matching it with your machine's operating system. For example, Windows software required a Windows machine. However, containerization has rewritten this narrative. Now it's ancient history. With containerization, you create a single software package, a container that gracefully runs on any device or operating systems. What's fascinating is that these containers seamlessly run while sharing the host operating system. Now, here's the techie part. The container engine is like a shadow, abstracted from the host operating system with limited access to underlying resources. Think of it as a super lightweight virtual machine. The beauty of this, the containerized application becomes a globetrotter, seamlessly running on bare metal, within VMs, or on the cloud platforms, without needing tweaks for each environment. Let's understand how is it different from virtualization. On one side, we have traditional virtualization. Picture this, it's like having multiple houses on a single piece of land, and each house or virtual machine has its complete setup, wall, roofs, and utilities. This setup, while providing isolation, can be resource intensive with each virtual machine carrying its entire operating system. Now let's shift gears to containerization, the modern day superhero. Imagine a high rise building where each floor represents a container. These containers share the same building or host operating system but have their private space or isolated user space. Here's the magic, they are super lightweight, don't carry extra baggage of a full operating system, and can swiftly move between different floors. With containerization technology, there's less overhead during startup and no need to set up a separate guest OS for each application since they all share the same OS kernel. Because of this high efficiency, containerization is commonly used for packing up the many individual microservices that make up modern applications. Containerization unfolds a spectrum of benefits, delivering unparalleled portability as containers run uniformly across diverse platforms. This agility, fostered by open source container engines, empowers developers with cross platform flexibility. The speed of containerized applications, known for their lightweight nature, reduces cost, boosts efficiency, and accelerates start times. Fault isolation ensures robustness, allowing independent operations without affecting others. Efficiency thrives as containers share the OS kernel and reusable layers, optimizing server utilization. The ease of management is achieved through orchestration platforms like Kubernetes, automating essential tasks. Security remains paramount as container isolation and defined permissions fortify the infrastructure against malicious threats. Containerization emerges not just as a technology but as a transformative force redefining how we build, deploy, and manage applications in the digital landscape. In closing, we have navigated the landscape of containerization, unlocking efficiency, scalability, and seamless deployment. Embrace the power of containers for a future ready, agile infrastructure. I hope you found this lesson interesting. See you in the next one. Thank you for watching.
Hello and welcome to this lesson centered around architecting cloud native solutions. I am Mahendra Mehra, your senior OCI instructor with Oracle University. Throughout this session, we'll embark on a comprehensive exploration of OCI's cloud native services, all within the context of an engaging and enlightening case study. So let's get started. Prisha, an Oracle client, engages with Steve, who's an Oracle consultant. Prisha initiates the conversation by expressing her concerns about migrating her static website to the cloud with new feature enhancements, specifically on Oracle Cloud Infrastructure. Steve reassures her, emphasizing the benefits of moving to Oracle Cloud Infrastructure and highlighting the potential to enhance the website's capabilities. Steve then asks Trisha about cloud native approach, to which Trisha expresses familiarity but admits she is unsure of its specifics. Steve offers to explain further, indicating his readiness to clarify any uncertainties Trisha may have. Steve proceeds to explain the concept of cloud native. He describes it as the approach to building and running applications that leverage the distributed computing capabilities of the cloud. Cloud native apps are designed to capitalize on the scale, elasticity, resiliency, and flexibility offered by the cloud. Steve highlights various technologies that enable cloud native development, including microservices and containers, Kubernetes and service mesh, serverless functions and APIs, Kafka, and DevOps practices, as well as CI/CD pipelines. He emphasizes that OCI provides tools and services to streamline development, reducing operational tasks, and enabling faster applications deployment. Ultimately, cloud native architectures facilitate loosely coupled systems that are resilient, manageable, and observable, empowering engineers to make impactful changes with ease. Trisha expresses her desire for a comprehensive overview of cloud native services offered by Oracle Cloud Infrastructure. Steve agrees, acknowledging the importance of understanding Trisha's requirements before delving into the details of OCI's cloud native service offerings. Let's use Trisha's website enhancement project as a case study to illustrate how various OCI service offerings can enhance the Vision Stays website and streamline future development and operations for Trisha's team. Let's understand Trisha's requirement in more detail. A hotel chain, Vision Stays, has a static website, that is its current form, and now they are interested in building a hotel booking facility to expand and enhance the website for their customers. They want to add a booking functionality, also some integration capabilities which will allow for third-party hotel aggregators to inquire about their hotel room availability and to book Vision Stays hotel rooms. They are looking at utilizing OCI Cloud Native solutions to host and enhance features of their website. This is what is the current state of the Vision Stays static website, and this is how it would appear with the new enhancements. Let's understand this entire case study in different steps. The first step focuses on migrating the static website to an OCI compute instance. This involves transitioning the website's files, including HTML, CSS, JavaScript, and media assets to a virtual machine provisioned within the Oracle Cloud Infrastructure environment. By utilizing a VM for hosting the static website, we leverage OCI's robust compute capabilities to ensure reliable performance and scalability. Subsequently, we'll incorporate an OCI load balancer to function as the front end of the website. The OCI load balancer acts as a traffic distributor, intelligently distributing incoming requests across multiple backend VM instances hosting the static website. This ensures optimal resource utilization and enhances website's availability and responsiveness. Additionally, the load balancer provides advanced traffic management features such as SSL termination, session persistence, and content-based routing, further enhancing the website's security and performance. It's crucial to establish IAM policies to govern the teams involved in deploying the website on OCI. IAM policies play a critical role in ensuring secure access and management of resources within OCI. By setting up IAM policies, we can control and restrict access to specific resources, ensuring that only authorized individuals or teams can perform certain actions. This helps maintain data confidentiality, integrity, and availability, ultimately enhancing the security posture of the environment. Now, once the static website is deployed on the Oracle Cloud Infrastructure platform, we can focus on implementing a microservices architecture to introduce new functionalities to the Vision Stays website. This approach involves breaking down the monolithic architecture into smaller, independent services known as microservices to enhance the scalability, agility, and maintainability. To achieve this, we'll employ various OCI services to facilitate different aspects of the microservices architecture. We can deploy certain microservices as containers within OKE, which is Container Engine for Kubernetes Service. OKE provides a scalable and flexible platform for managing containerized applications, offering features such as automated provisioning, scaling, and orchestration. Some microservices will be implemented using OCI functions. These functions execute code in response to events, providing a lightweight and scalable solution for handling specific tasks within the application. Container images and other artifacts required for the microservices will be stored in the OCI Container Registry and Artifact Registry. These services offer secure and scalable storage for container images and artifacts, ensuring efficient management and distribution across development and deployment environments. We can utilize Oracle API Gateway service to enable communication between the deployed microservices and external clients. API Gateway acts as a centralized entry point for accessing and managing APIs, providing features such as authentication, authorization, rate limiting, and traffic routing. By leveraging API Gateway, we ensure secure and efficient communication between microservices and external systems, enabling seamless integration and interoperability. We will leverage new serverless autonomous database for storing persistent data required by the microservices. Oracle's autonomous database offers a fully managed, self-driving database solution that automatically handles database provisioning, scaling, and patching, reducing operational overhead and ensuring high availability and performance. A web application firewall policy can be implemented to enhance the security of the Vision Stays website. Web Application Firewall provides protection against common web application threats and attacks, safeguarding the website from potential security vulnerabilities and breaches. The development to deployment process will be automated using DevOps Project and Resource Manager. DevOps Project enables streamlined collaboration and automation across the software development lifecycle, while Resource Manager facilitates infrastructure creation and management through code and templates, ensuring consistency and repeatability in infrastructure deployments. Service Mesh within OCI can be used to facilitate communication between microservices, which improves reliability and enhance observability within the distributed architecture. Lastly, we'll utilize core OCI services such as logging, notifications, and secrets encryption with OCI Vault to enhance operational visibility, monitor applications' performance, and ensure secure management of sensitive data and credentials. Now, since this video is getting a bit long, I'll take a break here and we will continue in the next part. I hope you're liking this video so far. See you in the next one. Thank you for watching. Welcome back. Let's continue from where we left off in the previous part. Let's now delve into the architecture blueprint for the Vision Stays online scalable application. This comprehensive diagram provides a high-level overview of the components and services integral to our case study solution. At the heart of our architecture are three microservices, namely Customer Service, Hotel Service, and Booking Service. They will collect and store customer details, manage information for Vision Stays hotels, and handle reservation booking respectively. To ensure seamless deployment and management, we propose containerizing each microservice and deploy them into a Kubernetes cluster managed by OCI's Container Engine for Kubernetes, also known as OKE. To extend functionality to third-party vendors, we'll create two Oracle functions, namely create booking function and get hotel details function, and secure them using API gateway implementation. This centralized gateway acts as a protective barrier, regulating access to our backend microservices and ensuring that all incoming requests are handled securely and efficiently. Internally, these functions will interact with the microservices that are deployed within the OKE. All data generated by these microservices will be stored in Oracle Autonomous JSON databases instances. In alignment with our earlier discussion, the front end of our website will be hosted on OCI Compute Virtual Machine Instance. As previously mentioned, this setup will be complemented by a load balancer implementation to efficiently distribute traffic and ensure scalability. Also, as previously emphasized, security is of paramount importance. Our strategy involves bolstering the web application's defenses through OCI Web Application Firewall, ensuring robust protection against potential threats. In our journey to streamline the build, test, and deployment processes, we turn to DevOps practices and the OCI DevOps project resource as our trusted allies. Every code commit initiates a series of action within our CI/CD pipelines. As changes are pushed to our OCI DevOps code registry, build triggers automatically kick off build runs, facilitating creation of new artifacts or container images. These freshly minted assets are then securely stored in our artifact and container registry, which are ready for deployment. During the execution of our deployment pipelines, these stored artifacts or container images are seamlessly pulled from the registry. This ensures that the deployment process is smooth and efficient, with the latest version of our application components readily available for deployment. With such automation in place, we are not just deploying code, we are implementing deployment strategies like blue-green and canary deployments, ensuring minimal disruption and maximum reliability. This strategic approach enables us to deliver updates swiftly and confidently, meeting the evolving needs of our users while maintaining the stability of our application. Additionally, the booking service can utilize OCI's notification and streaming service to send email notifications to the hotel administration team for new bookings and store messages for downstream analysis. To safeguard sensitive credentials such as database passwords, we can leverage OCI Vault service for secure storage. In the next step, we'll establish events, monitoring, alerting, and logging systems to meticulously track the performance and health of the Vision Stays application. These observability services play a critical role in providing real-time insights into the application's operation and overall health. With OCI Event Service, developers can easily trigger code execution through functions, write to streaming service, or send alerts using notification, enabling intelligent response automation to changes within the infrastructure. Monitoring tools continuously access various metrics such as CPU and memory utilization, network traffic, and response times, allowing us to promptly identify any anomalies or performance bottlenecks. Additionally, alerting mechanisms can be configured to notify the appropriate personnel in the event of unusual activity or critical system issues. Furthermore, logging systems capture and store detailed information about applications' events and user interactions. This comprehensive logging data enables us to conduct thorough analysis, troubleshoot issues efficiently, and gain valuable insights into user behavior and system performance. By implementing these observability services, we can proactively monitor the Vision Stays application, promptly address any issues that may arise, and ensure optimal performance and reliability for our users. In summary, our architecture blueprint for the Vision Stays website case study solution integrates a comprehensive suite of OCI cloud native solutions, including microservice architecture, containerization, and container orchestration. Leveraging serverless computing and DevOps services, we've streamlined development processes with efficient CI CD pipelines. Furthermore, the inclusion of API Gateway ensures secure access to backend microservices, while OCI core services provide essential infrastructure support. Combined with observability tools for enhanced monitoring, our solution embodies the pinnacle of cloud native practices, empowering Vision Stays web application to scale and innovate with confidence in today's dynamic landscape. I hope you found this case study interesting. See you in the next lesson. Thank you so much for watching.
Hello and welcome to this introductory lesson on OCIR, also known as Oracle Cloud Infrastructure Registry. I am Mahendra Mehra, your senior OCI instructor with Oracle University. In this session, we'll delve into the key features, benefits, and functionalities that make OCIR an essential tool for containerized application development and deployment. Let's get started. What is OCIR? OCIR is an Oracle managed registry designed to simplify the development to production workflow for developers. It offers a range of functionalities, serving as a private Docker registry for internal use, where developers can easily store, share, and manage container images. The strength of OCIR lies in its high available and scalable architecture. Leveraging OCI to ensure reliable deployment of applications, developers can use OCIR not only as a private registry but also as a public registry, facilitating the pulling of images from public repositories for users with internet access. What sets OCIR apart is its compliance with the Open Container Initiative standards, allowing the storage of container images conforming to the OCI specifications. It goes a step further by supporting manifest lists, sometimes known as multi-architecture images, accommodating diverse architectures like ARM and AMD 64. Additionally, OCIR extends its support to Helm charts. Security is a priority with OCIR, offering private access through a service gateway. This means that OCI resources within a VCN in the same region can securely access OCIR without exposing them to the public internet. Let's explore the key advantages offered by OCIR. Firstly, OCIR seamlessly integrates with the container engine for Kubernetes, ensuring a cohesive container management experience. In terms of security, OCIR provides flexibility by allowing registries to be either private or public, giving administrators control over accessibility. Furthermore, it is intricately integrated with IAM, offering straightforward authentication through OCI identity. Another notable benefit is regional availability. You can efficiently pull container images from the same region as your deployments. For high performance, availability, and low latency image operations, OCIR leverages the robust infrastructure of OCI, enhancing the overall reliability of image push and pull operations. OCIR ensures anywhere access, allowing you to utilize container CLI for image operations from various locations, be it on the cloud, on premises, or even from personal laptops. Additionally, OCIR implements repository quotas. In each enabled region for your tenancy, you can establish up to 500 repositories with a cumulative storage limit of 500 GB. Each repository is capable of holding up to 100,000 images. Importantly, Charges apply only for stored images. Before we move further, let's take a look at container registry concepts. What are images? Image is basically a read-only template with instructions for creating a container. It holds the application that you want to run as a container along with any dependencies that are required. Container registry is an open container initiative compliant registry. As a result, you can store any artifacts that conform to Open Container Initiative specifications, such as Docker images, manifest lists, sometimes also known as multi-architecture images, and Helm charts. Let's understand what is a repository. It's a meaningfully named collection of related images which are grouped together for convenience in a container registry. There are different versions of the same source image which are grouped together into the same repository. For example, as you can see, we have a repository called Mahindra_project/Acme web app. Now you can have multiple images stored under this repository. The only thing that you need to keep changing is the image version. Every image version is given a tag, and the tag uniquely identifies the image. As in this case, we have two images for the Acme web app, which is 4.6.1 and 4.6.2. Depending upon your need, a repository can be made private or public. One important thing to note is that the user need to have an OCI username and authentication token before being able to pull an image from the OCIR. When working with repositories and container registry, you will find it helpful to have a clear understanding of following terms and how they relate to each other. Starting with the region key. The region key identifies the container registry region that you are using. For example, as you can see here, the IAD specifies the US East Ashburn region, whereas the US Phoenix one specifies the US West Phoenix region. A tenancy namespace is an auto-generated random and immutable string of alphanumeric characters. For example, the namespace of Acme Dev tenancy might be a random string, something like this on the screen. To find out the tenancy namespace of the current tenancy, on your OCI console, click on the profile menu and click on the tenancy option. The tenancy namespace can be retrieved from the value of your object storage namespace field. Repository name. The repository name is the name of repository in container registry to and from which you can push and pull images. Repository names can include one or more / characters and are unique across all the compartments in the entire tenancy. You should note that although a repository name can include / characters, the / does not represent a hierarchical directory structure. It is simply one character in the string of characters. As a convenience, you might choose to start the name of different repositories with the same string. As you can see in the example, we have started all the repos with the name project01, perhaps ending in a / such as project01/. Such string is sometimes called as repository name prefix. But a repository named project01/Acme web app may not have a relationship with the project name project01/Acme web app/component2. Registry identifier. A registry identifier is the combination of your container registry region key and the tenancy namespace. It has the following structure: region key.ocir.io/tenancy namespace. As you can see in the example, we have a region key for the US Ashburn region, iad.ocir.io/a random alphanumeric string for our tenancy namespace. Moving on, a tag or an image tag is a string used to refer to a particular image in a known registry. The term image name is sometimes used as a shorthand way to refer to a particular image in a particular repository. In this context, an image has the structure repository name along with tag separated by colon. As you can see from the example, we have an image name with the repository name as project01/Acme web app separated by the tag 4.6.3. A tag can be a numerical value or it can be a string, as in this case. Third example here, we can see that the repo name is my hello app and colon separated by the image tag, which is latest. An image path is a fully qualified path to a particular image in a registry. It extends the repository path by adding tags associated with the image. It has the following structure: regionkey.ocir.io /tenancy namespace /repo name :tag. And you can always refer Oracle official documentation to identify region key for the region you're working in. From the examples, we can see that there are two image paths belonging to the US Ashburn region, whereas the third one belongs to the US West Phoenix region. In conclusion, Oracle Cloud Infrastructure Registry, with its seamless integration, robust security measures, regional accessibility, and efficient image management, stands as a pivotal tool for modern containerized workflows. I hope you found this lesson useful. See you in the next one. Thank you for watching. Hello and welcome to this lesson on managing Oracle Cloud Infrastructure Registry. My name is Mahendra Mehra and I am a Senior Training Lead and Evangelist with Oracle University. Managing OCIR can be done in three ways, starting with managing the repository itself, followed by managing the images within the repository, and last but not the least, managing the overall security of your repository alongside the images. Let's understand each one in more detail. You can create an empty repository in a compartment and give it a name that's unique across all the compartments in the entire tenancy. There is a limit to the number of repositories you can have in a given region in a tenancy. So when you no longer need a repository, it makes sense to delete it from the Oracle Cloud Infrastructure Registry. Make a note that when you delete a repository, it can take up to 48 hours for the deletion to take effect and for the storage to actually be released. When you create a new repository in Oracle Cloud Infrastructure Registry, you specify the compartment in which you want to create it. Having created the repository in one compartment, you can subsequently move it to a different compartment. The reasons can be many. It can be to change the users who are authorized to use the repository or to change how the billing for a repository is charged. Let's have a look at how to manage images. You can view the images stored on OCIR using the OCI console or using Docker images command from your Docker client after logging in into the OCIR repo. To push an image, you first use the docker tag command to create a copy of the local source image as a new image. As a name for the new image, you specify the fully qualified path to the target location in your container registry where you want to push the image, including the name of a repository. In order to pull an image, you must be logged in into the OCIR registry using the auth token and use the docker pull command followed by fully qualified name of the image you wish to download on your Docker client. When you no longer need an old image or you simply want to clean up the list of image tags in a repository, you can delete images from the Oracle Cloud Infrastructure Registry. You can undelete an image you've previously deleted for up to 48 hours after you deleted it. After that time, the image is permanently removed from the container registry. You can set up image retention policies to automatically delete images that meet particular selection criteria. Criteria can be images that have not been pulled for a certain number of days or images that have not been tagged for a certain number of days. It can also be images that have not been given particular Docker tags specified as exempt from the automatic deletion. There's an early process that checks images against the selection criteria, and any that meet the selection criteria are automatically deleted. In each region in a tenancy, there's a global image retention policy. The default criteria of the policy is to retain all images so that no images are automatically deleted. However, you can change the global image retention policy so that the images are deleted if they meet certain criteria that you specify. A region's global image retention policy applies to all the repository within that region, unless it is explicitly overridden by one or more custom image retention policies. Only one custom image retention policy at a time can be applied to a repository. If a repository has already been added to a custom retention policy and you want to add repository to a different custom retention policy, you have to remove the policy from the first retention policy before adding it to the second one. Make a note, the global image retention policy are specific to a particular region. To delete images consistently in different regions in your tenancy, you need to set up image retention policies in each region with identical selection criteria. If you want to prevent images from being deleted on the basis of Docker tags they have been given, you need to specify those tags as exempt in a comma separated list. When you want to clean up the list of images in a repository without actually deleting the images, you can remove the tags from the images in OCIR. Removing images is referred to as untagging. During the deployment of an application to a Kubernetes cluster, you'll typically want one or more images to be pulled from a Docker registry. In the application's manifest file, you specify the image that you wish to pull, the registry to pull them from, and the credentials to use when pulling the images. If you want the application to pull images that reside within the container registry, you will have to perform two steps. The first one is you have to use the kubectl to create a Docker registry secret. The secret contains Oracle Cloud Infrastructure credentials to use when pulling the image. The next step is you have to specify the image to pull from the container registry, including the repository location and the Docker registry secret to use in the application's manifest file. While managing security, you are given fine-grained control over the operations that users are allowed to perform on repositories within the container registry. Using the concept of users and groups, you can control repository access by setting up identity access management policies at the tenancy and at the compartment level. These are examples of some of the policies that you can use to control access to your container registry. You can write policies to allow, inspect, read, use, and manage operations on the repository based on the requirements. Before you can push and pull Docker images to and from the container registry, you must already have an Oracle Cloud Infrastructure username and an authentication token. It is not uncommon for the operating system packages included in images to have vulnerabilities. Managing these vulnerabilities enables you to strengthen the security posture of your system and respond quickly when new vulnerabilities are discovered. You can set up Oracle Cloud Infrastructure Registry to scan images in a repository for security vulnerabilities published in the publicly available Common Vulnerabilities and Exposure databases. To perform image scanning, Container Registry makes use of the Oracle Cloud Infrastructure Vulnerability Scanning Service and Vulnerability Scanning REST API. You need to define certain policies for scanning images for vulnerabilities. Policies like to allow the vulnerability scanning service to read the repositories within your tenancy or the compartment. Again, policy like to allow vulnerability scanning service to read compartments within your tenancy or any parent compartment where you're managing your repository. Preparing for container registry. Before you can push and pull Docker images to and from Oracle Cloud Infrastructure Registry, you need to have the following in place. The first thing is your tenancy must be subscribed to one or more of the regions in which the container registry is available. You can check the same within the Oracle documentation. The next thing is you need to have access to the Docker command line interface to push and pull images on your local machine. The third thing is users must belong to a group to which a policy grants the appropriate permission or belong to a tenancy's administrator group which by default have access permissions on the container registry. Lastly, user must already have an Oracle Cloud Infrastructure username and an authentication token which enables them to perform operations on the container registry. To wrap up, in this lesson we covered OCIR in greater details and learned how to manage OCIR along with required IAM policies. We also understood the scanning image security feature to detect vulnerabilities earlier in the software development lifecycle. I hope you found this lesson useful. See you in the next one. Thanks for watching. Hello and welcome to this lesson on OCIR images concepts. I am Mahendra Mehra and I am a senior training lead and evangelist with Oracle University. So before I talk about OCIR images, let's try to understand what is Open Container Initiative, also abbreviated as OCI. The Open Container Initiative is an open governance structure for the express purpose of creating open industry standards around container formats and runtimes. It was established in June 2015 by Docker and other leaders in the container industry. Following the Docker's release, a large community emerged around the idea of using containers as the standard unit of software delivery. As companies started using containers to package and deploy their softwares frequently, Docker's container runtime did not meet all the technical and business needs that the engineering teams could have. So, in response to this, the community started developing new runtimes with different implementations and capabilities. To make sure that all container runtimes could run images produced by any build tool, the community started the Open Container Initiative to define industry standards around container image formats and runtimes. Oracle joined the Open Container Initiative to promote and achieve the initiative's primary goal, that is, to host an open source technical community and build a vendor neutral, portable, and open specification and runtime for container based solutions. The OCI specification is divided into two parts. One is the image specification and the other one is the runtime specification. Now these two covers the different phases of the container lifecycle. The OCI image specification defines how to create an open container initiative image, and the runtime specification outlines how to run a file system bundle that is unpacked on the disk. At a high level, an OCI implementation would download an OCI image, then unpack that image into an OCI runtime file system bundle. At this point, the OCI runtime bundle would be run by an OCI runtime. So it's important to understand that our Oracle's container registry is an implementation of that OCI runtime specification. Let's take a closer look at the OCI specifications. Let's talk about image spec. The image spec defines how to create an OCI image, and which includes things like image manifest, file system serialization, and image configuration. The image manifest basically provides a configuration and set of layers for a single container image for a specific architecture or an operating system. File system serialization talks about how to serialize a file system and file system changes like removed files into a blob called a layer. The image configuration specification outlines the JSON format describing images for use within a container runtime and execution tools and its relationship to file system change sets described within the layers. Talking about runtime specification, the OCI runtime specification defines how to run the OCI image bundle as a container. So in a nutshell, the container runtimes does some of the following tasks. Tasks like container image management, container lifecycle management, container creation, and container resource management. Let's have a look at some of the popular container runtimes. Containerd is a CNCF project and it manages the complete container lifecycle of its host system. Rocket is an application container engine developed for modern production cloud-native environments. CRI-O is an implementation of the Kubernetes container runtime interface to enable using the Open Container Initiative compatible runtimes. It is a lightweight alternative to using Docker as the runtime for Kubernetes. Runc is a CLI tool for spawning and running containers according to the OCI specification. It was developed by Docker and donated to OCI as the first OCI runtime spec compliant reference implementation. Some of the runtimes like Rocket does most of the task by itself, whereas runtimes like Containerd does some of the high-level functions and uses other runtimes like Runc for some of the low-level tasks. Let's understand the OCI image layout specification. The OCI image layout is a slash-separated layout of OCI content addressable blobs and location addressable references. Now this layout may be used in variety of different transport mechanisms, for example archive formats like tar or zip, shared file systems environment like NFS, or networked file fetching, for example HTTP, FTP, and rsync. The OCI image layout consists of OCI layout file. This JSON object serves as a marker for the base of an open container image layout and to provide the version of the image layout in use. The index.json file is a must file to have in the OCI image layout. This file is an entry point for the references and descriptors of the image layout. The image index is a multi-descriptor entry point. Object names in the blob subdirectories are composed of a directory for each hash algorithm, the children of which will contain the actual content. Now, given an image layout and the references, a tool can create an OCI runtime specification bundle by following the references to find a manifest, possibly using the image index and applying the file system layers in the specified order, later converting the image configuration into an OCI runtime specification config.json. So at a high level, the combination of image manifest, image configuration, and one or more system serializations known as layers is called the OCI image. Let's talk about layers within an image. A layer is read-only, and a layer contains the differences between the preceding layer and the current layer. On top of the layers, there is a writable layer, which is also called the container layer. Any changes to the file system during the container runtime are only returned to this layer, which includes addition, modifications, and deletions of files without changing the content of the original image at the lower layers. This greatly improves the efficiency of image distribution. Container layer exists only during the container runtime, and it will be deleted when the container is deleted. Multiple different containers can be created from the same image, and only multiple different writable layers need to be created. Containers that have been changed at runtime can also be repackaged into new image by adding the writable layer to the read-only layers of the new image. After an image has been pushed to an OCIR repository, to make sure you are working with the correct image or to identify the image that you no longer need, you could easily view and find out detailed image information including their layers in the Oracle Cloud Infrastructure Registry. So this is a snapshot from the OCIR where if you select a particular image, you get to see all the layers associated with that image. So putting it all together, let's summarize the entire learning using an illustration. The developer creates a Docker file which consists of syntax for defining the steps needed to create the image and run it. We use the docker build command to create the image according to those specifications. We then push the image to a Docker registry, in our case OCIR, that is Oracle Cloud Infrastructure Registry, also known as OCI Container Registry. And since the Docker image includes all the elements needed to run an application as a container, users will run an image which builds one or more instances of that respective container that is then deployed to a Docker runtime such as Oracle Container Engine for Kubernetes cluster, Oracle Functions, or perhaps running your own compute virtual machines. So to wrap up, in this lesson we learned about images that is being maintained in the OCI Container Registry based on those standardized OCI specifications, and then looked at a high-level workflow involving the building and running of Docker image. I hope you found this lesson useful. Thanks for watching. Hello and welcome to this demo on managing Oracle Cloud Infrastructure Registry or OCIR. In this multi-part demo, we will explore how to effectively manage repositories and container images within OCIR. In this part 1 demo, we will be covering a range of tasks including creating a repository, listing repositories, getting a repository's details, editing a repository, moving a repository between compartments, and deleting a repository. These operations are essential for maintaining a well-organized collection of container images and repositories. Let's dive into the details. I have logged in into my OCI console, and to tell you, the user account using which I'll be performing the demo is part of the administrators group. In case you are trying to shadow these demos, make sure that the user you are using to run the demo have the required policies granted to them. Let's begin with the first task, that is to create a container registry repository. In order to create a container registry repository, we must click on the navigation menu and go to the developer services. Within the containers and artifacts section, you'll find the container registry. So let's click on container registry. Now this opens up the container registry page for you. Now you must ensure that you have selected the right region where you wish to create the container repository. In my case, it is US West Phoenix region. You must also ensure that you have selected the right compartment where you have the permissions to work in. In my case, it is OCIR-OKE-demo compartment. As you can notice, currently there are 0 repositories, 0 images, there are no layers. Of course, if there are no images, there won't be any layers, and 0 bytes utilized. Let's start by creating a repository. To create a repository, let's click on the Create Repository button. This opens up a Create Repository panel for us, and the options in the panels are, firstly, it allows you to create in compartment, that is, you can decide to change the compartment where you want to create the repository. I'll stick to the original plan. And under the access information, you can choose from private or public option, right? There are a few things to note about private and public option. Whether the repository is public or private repository, you can only make the repository public if you belong to the tenancy administrators group or have been granted the repository manage permission, right? And also, if you make the repository public, any user with the internet access and the knowledge of appropriate URL can pull the image from the repository. If you wish to make your repository private, then you, along with other users belonging to the tenancy's administrator group, can perform any operation on this repository. So let me start by creating a private repository. Let me give it a suitable name. So I have given a name to my repository, which is OCI-repo-private/nginx. The name that you enter must be unique across all the compartments in the tenancy, and you must avoid entering confidential information. Assigning tags are optional. You can go for a free-form tag or you can use a defined tag. That's all up to you. In my case, I'll leave it blank. Let's click on Create. Well, as you can see, the repository has been created. The count has been increased to 1, but still there are no images in my repository as of now. Now let me go ahead and create a public repository. So let's click on Create Repository. Let's choose the public access option and give repository a suitable name. Alright, so I've given my repository name as OCI-repo-public/MySQL, where I'll be storing MySQL images. Let's go ahead and click Create. And there you go, my public repository has been created. So at present, we have 2 repositories in our container registry within the US West Phoenix region and OCIR-OKE-demo compartment. Now the next task is to find out how to list the repositories in container registry. Basically, your permission controls which repositories you can list. If you belong to the administrators group, you can list any repository in the tenancy. But if you're not part of the administrator group, then it is the IAM policies granted to the user group that defines which repositories you can list within the tenancy. In our case, we have 2 repositories. One is the Nginx with private access and the other one is MySQL with public access. Now on the screen, as you can see, we can view the MySQL public access repository, right? But what about the Nginx? Basically, you'll have to come to this location and click on this drop down over here under the repositories and images label, and you can notice that we have 2 repositories listed. One is the Nginx private and the other one is MySQL public. So let's click on Nginx private, and if you notice, we get to see the details of the Nginx private repository. Let's understand what all details we get to know about a particular repository. Details such as the user who created the repository, when was it created, what is the kind of access the repository has, the repository's unique identifier, the namespace in which the repository is created, the total size that the repository is holding, basically the container images size, what is the billable size in GB, right? And again, the last push, basically when was an image pushed into this repository. Currently there are no images, it's not applicable for empty repository.
Again, we have a readme section. So basically you can edit this information and provide some detailed information as to what this repository is all about. Let me quickly go ahead and type some information here. Alright, so as you can see, I have populated basic information about this repository and click on Save Changes. And this is where the README information about this repository gets populated, right? This was about how do you list a repository. Let's go back to the MySQL. So let's click on this drop down and select MySQL. But if you notice, there are no images in these repositories. So there is no expansion sign over here. Later on in the demos, when we push images to these repositories, you will find them over here. Let's click on MySQL and see. You can notice that it shows that it's a public repository. Having created a repository in the container registry, we can edit its properties. For example, we might want to change the access of a repository from private access to public access. As you can see on the screen, we have this MySQL repository selected, which is a public repository. And if we wish to change its access type to private, we can always do that by clicking on the Change to Private button. When I click on Change to Private, it changes to a private repository. As you can see, the access type has changed to private. Similarly, I can switch it back to public by clicking on Change to Public. As I click on Change to Public, the access has changed back to public access. This is how you can change the access types. Now, apart from changing the access type, what else we can do is we can click to add scanner. Basically, this enables image scanning by adding an image scanner to the repository, which we'll be discussing in more detail in the later demos. We can also click on Move Compartment button to move our repository from one compartment to another. For example, if I wish to move this repository from the OCIR OK demo compartment to some other compartment, then in that case, I'll click on Move Compartment, and I simply have to choose a compartment from the list of compartments where I have the permission to move this particular repository into. Alright, so let me show it to you in action by moving this repo from the OCIR OK demo to, let's say, CTDoc compartment. Let me click on CTDoc over here and let me click on Submit. As you can notice, the number of repositories has reduced to 1 in my OCIR OKE demo compartment. Now if we take you to the CTDoc compartment, now if you click on the list of repositories and images, you notice that OCI-repo-public/MySQL repository has been moved to this compartment named CTDoc. Alright, so let's click on this repository over here. And let me move it back to the OCIR OK demo compartment. So in order to do that, I'll simply click on Move Compartment and I'll choose my compartment from the list, which is over here, and click on Submit. Now, if you go back to the OCIR OK demo compartment, you'll notice that the list of repositories says there are 2 repositories and I have both my repositories available over here. So let's find out how to delete a repository from the container registry. Of course, you must delete registry because there is a limit to the number of repositories that you can have in a given region in a tenancy. So when you no longer need a repository, you must delete it. And any images in the repositories are deleted when you delete the repository. Let me just quickly show you by deleting a repository. The best way would be to go to a repository which has some images in it. Let me go to the CTDoc compartment, which I showed you earlier. And we have 3 repositories over here. Let me select one of the repository which has some images in it. For example, if I select the MySQL repository over here, this is in the CTDoc compartment. This is not similar to the one that we created in the OCIR OK demo compartment. This is a separate repo. If you notice, we have an image in this already, right? So let me go ahead and delete this repository. So when I delete this repository, it will also delete the image that it holds. For example, the image that it holds is MySQL with the tag 8.0.31, right? Let me click the repository and let me click on delete repository over here. So when I click on delete repository, it will ask me to confirm if I wish to delete this repository, also remove one of the associated images. When you click on delete, basically you confirm the deletion. And there you go, the repository and the image has been deleted. So just a quick note, although we have deleted the repository from the interface, but it might take up to 48 hours for the deletion to take effect and for the storage to be released. Well, that's it from this demo where we saw how to create a repo, list repositories, get repositories details, edit repository properties, move them between compartments, and how to delete a repository. I hope you found this demo useful. See you in the next one. Thank you so much for watching. Hello and welcome to this part 2 video on managing OCIR, where we'll be performing tasks to push and pull images to and from OCIR repositories. So let's dive in. Well, we are back to the OCI console. This is our OCIR repository page. And if you remember from the last demo, we had created two repositories. One is for the Nginx, which has private access, and the other one is our OCI repo public/MySQL repo, which is having public access. Now we'll be starting by pushing images to the OCIR repositories that we created, and we'll be using the Docker CLI. But in this case, I'll be using the Cloud Shell, which already comes inbuilt with a Docker CLI. So let me go ahead and launch Cloud Shell. This will take some time for my Oracle Cloud Shell machine to spin. Let's wait for that to happen. Cloud Shell machine is up, and here is my prompt. Let me clear the screen. Remember, it is your permissions which control the images that you can push to the container registry. And if you belong to the administrators group, you can push images to any repository in the tenancy. To push images to the container registry using the Docker CLI, the first thing that you must have is the auth token. Let me show you how to create an auth token. Let me first minimize this Cloud Shell console. In order to create an auth token, we must click on the profile menu in the top right corner, and we must click on My Profile. And then under the resources section, we must click on auth tokens. As you can see, currently there are no tokens within the auth tokens. Let's quickly go ahead and create one auth token. Let's click on generate token for that and give a suitable description. Let's say I give it OCIR token, and let's click on generate token. I will copy this token and save it in a notepad file because I'll be using it later on. Let me click on close. Now let me go ahead and restore the Cloud Shell window. Now in this terminal window, let me log in into the container registry by entering the docker login command. So let me type docker login and then specify the container registry where I wish to log in into. The syntax is regionkey.ocir.io. As you can notice, the region that I'm working in currently is the US West Phoenix region. The region key for US West Phoenix is phx. I'll write phx.ocir.io and hit enter. In case you're working in a different region, you can always find your region key by visiting this page over here, and it shows you all the region key for the different regions. In my case, it's US West Phoenix. So as you can notice, the US West Phoenix region key is phx. Similarly, US East Ashburn has the region key IAD, right? And all other regions that support OCIR has their region keys available over here, right? So if you're working in a particular region, you can choose your region key from this particular page, which is available under the container registry official documentation. Let me go back to the console. So when you hit the docker login command, the first thing that it prompts you for is the username. The username must be entered in the format tenancy namespace / your username. Now what is a tenancy namespace? Tenancy namespace is the auto-generated object storage namespace string of your tenancy, which you can find in the tenancy information page. So let me quickly show you that information. In order to check your tenancy namespace, click on your profile menu, go to your tenancy information page. Let me quickly minimize the Cloud Shell terminal. And so as you notice, this is the tenancy namespace that you must provide. It will be different in your case. And just in case if your tenancy is federated with Oracle Identity Cloud Service, in that case, your format should be tenancy namespace / Oracle Identity Cloud Service / username. Well, let me restore this Cloud Shell terminal and let me go ahead and hit enter for the username. The password here is basically the auth token that we created earlier. I had copied it, so I'll paste it over here. And remember, when you paste the password, it won't show up on the screen. You just need to hit enter. As you can see, it says login succeeded. Now, since I'll be using the Cloud Shell terminal for a while, let me quickly maximize it. The next step that we'll be doing is to check for any existing Docker images in our Cloud Shell machine. Let me run the command docker images. As you can see, there are no images in my local repository. So let me quickly download the latest images for both Nginx and MySQL from the Docker Hub. In order to download them from the Docker Hub, let me quickly run this command: docker pull Nginx, and by default it will pull the latest Nginx image. As you can see, it says using default tag latest. The Nginx latest image has been downloaded. Let me quickly do a docker images command again. Docker images to check if the image has been downloaded. Well, as you can notice, the Nginx latest image has been downloaded and the size is 187 MB. Let me also download the MySQL image. Let me run docker pull MySQL. As you notice, it's pulling the latest image for MySQL. And there you go, our MySQL latest image has been downloaded. If I do a docker images now, I get to see both my images, Nginx and MySQL, available in my local repository with the tag latest. Let me quickly clear the screen. Now the next step will be to push these images into their respective repositories that we have created in the container registry. Let me quickly minimize this terminal. And let's go to the container registry. Let's click on developer services, go to container registry. As you can notice, we have our two repositories, and let me click on Nginx first and let's push an image into the Nginx private repository. Let's click on Nginx over here. So we need to push an image into this repository now. In order to push an image into the Nginx repository, we'll have to tag our Nginx image that we just downloaded. So in order to tag the image, we'll be using the docker tag command. So the command is docker space tag and the image that you wish to tag. So in our case, it's the Nginx latest image. What I'll be doing is I'll be using the image ID. So it's not required that you use the full ID. We can use the first four letters. That's sufficient. Let me use BC64, which is the image ID's first four letters, followed by the fully qualified path to the target location in the container registry where we want to push the image. The format for the target tag basically is regionkey.ocir.io. Region key, we already know it's phx.ocir.io / separated by the tenancy namespace. In my case, it is int Oracle Rohit and / separated by the repo name. As you can notice, the repo name is oci-repo-private/nginx. I'll simply copy this information from here and I'll paste it over here. And then colon separated by version. Version is the identifier that you want to give the image in the container registry. We can leave it as latest or we can specify a number to it. So I'll leave it as latest. Let me go ahead and hit enter. And as you can see, it has returned me the prompt, which means the command ran successfully. Just to confirm that the Docker image has been correctly tagged on the client machine, we must enter the Docker images again and verify from the list of images, right? So let me go ahead and run Docker images. If I hit enter, let me quickly maximize the screen. And if you notice, I just ran the Docker images command, and alongside the Nginx original image, I have this new tagged image, which has the format of our fully qualified path, right? And if you notice, the image IDs are same. Basically, the new tagged image is just the reference to the original image. This means we have tagged our image correctly. Now it's time to push this image to the OCIR repository. So in order to push the image to the OCI repository, let me first clear the screen. The command is docker push and the target tag. I'll first bring up the Docker images, and I'll be using this target tag to push this image to our container repository. So let me go ahead and write docker push and simply paste this tag. All right, so I'll be using the command docker push the target tag, which is phx.ocir.io slash the tenancy namespace slash the repository name colon the version, right? So it is latest. Let me quickly type latest over here and go ahead and hit enter. As you can see, the push operation is in progress and it's pushing this image, Nginx latest image, to this repository. The push operation completes, it returns you the digest of the image, SHA-256 digest. Let me quickly minimize it and let's check if the image is now seen in the Nginx private repository that we had created. Let me go ahead and quickly refresh. Alright, so let's click on the list of repo, and now as you can notice, under the OCI repo private Nginx repository, we have this new image that's available with the tag latest. When I click on that image, as you can see, we have the Nginx image with the latest tag available in our container registry repository. And with that, we have successfully pushed an image into the private repository. Now let me go ahead and show you a demonstration of how to push an image in a public repository. Let's restore the Cloud Shell terminal. Let me maximize it. Let's start by running the docker images command. I have this MySQL image with the tag latest, which I'll be pushing to my OCIR repo. Let me write the docker tag command and let me use the image ID for this image, which is 2D9A. Remember, like I said, you can use the first 4 letters, that is fine because it's a unique ID that every image gets. Let me go ahead and populate the target tag. The target tag is phx.ocir.io slash separated by the tenancy namespace slash separated by the repository name. The repository name is something that we'll get from here that we just created. So let me go to the repository first. And let me quickly copy the repository name. Let me paste the repository name here. Let me maximize this terminal. And let's also assign the version, which is latest, and let's hit enter. Well, the prompt has returned, which means it has successfully tagged the image. Now let me go ahead and run the docker images command, and if you notice, we have a new MySQL image which has been tagged, and if you notice, it's referring to the original MySQL image as the image IDs are similar. Now I have to just push this image to my public repository, and in order to push, we will be using the docker push command. So let's use the docker push command followed by the tag. So let me use this and colon separated by the version. When I hit enter, this will start pushing this image to the OCIR container registry where we have created the repository OCI repo public /MySQL. Let me hit enter. And as it says, the push refers to repository phxocir.io in the tenancy namespace int orkel and within the repository OCI repo public /MySQL. The push operation has completed successfully. It has returned a digest, right, which is the SHA-256 digest. Let me go back to the container registry and let's just see if this image has been pushed. Let's click on the MySQL repo from the list. As you can see, the image is not currently being seen. Let me quickly refresh this page. The page has refreshed. Let me click on the list from the drop down menu and see if I can see that image. Yes, as you can notice, we have this MySQL latest image under the MySQL public repo. Let me minimize this terminal and let's click on this MySQL latest image. And as you can notice, we have this MySQL latest image that's available in the MySQL repository. So we were able to push two images. One is the Nginx in a private repo and one was for MySQL in a public repo. Since this video is getting long, we will continue in the next one. See you there and thank you so much for watching.